Greenfield, just in case you didn't know who he was. He's going to tell us about the development and future of Python skills.
So I'd like to thank the organizers for inviting me to speak, and also particularly to thank Tom Robitaille for setting up what I think has turned out to be a fantastic workshop. And I think it succeeded in many levels, and I hope we can do this sort of thing regularly. This should not be the only time we do something like this. So I was going to talk a little bit about how we got involved in Python and what we've done up to now, and spend a fair amount of time talking about what we see its role for JWST, what our current work is, and intermingled with that, what I see is some of the bigger challenges, and they're not all technical. So to start with the prehistory, by the time HST was launched, we were writing all our data analysis calibration pipeline software for the IRAF system, and while it worked for us to do that, this is actually before my time in this branch, but it quickly grew. There quickly grew some dissatisfaction working this way, for a number of reasons listed here. The developers felt somewhat uneasy writing in a language that nobody else uses outside of a small, band of people in astronomy. The architecture is pretty closed, and the facilities began to stagnate immediately. At the time it was developed, it was sort of current, but the facilities in IRAF never really moved along with the rest of the software world. So by about the mid-90s, there was more and more desire to see, was there a way out of this? And it partly started out with an effort called Open IRAF, but it quickly became clear that that wasn't really going to work. And so, what else could we do? So, actually,
by non-standard languages.
SPP, you mean?
No, I know that, but I bet you that there are three-quarters of the people who never heard of it.
Oh, really?
Wow.
Yeah. So maybe just a few seconds. IRAF writes all its applications, almost all its applications, in a language called SPP, which is a custom language, which is actually pre-processed into some, mostly Fortran 66. And its scripting language is, well, that's not what you usually deal with unless you want to go into the debugger. And and the scripting language is its own custom language, the CL, it's commonly known. Thanks for raising that. And so we were wondering, so it was actually a movie that gave us some inspiration about how to get out of this. And the clue was in the sky there, snake. That was, that was a subliminal message of how we were actually going to do that. So how was the Python foot in the door? We got started in thinking, well, at the very least, we could come up with a better scripting language for IRAF. And there was a bigger motive behind this. I'll get to that later. And Python is what we tried. There were people at, as I recall, an ADAS in Germany that were touting Python, so we thought, well, let's give that a try. And in doing this, what turned out to be PyRAF, we were extremely impressed with what Python could let you do, and very quickly wanted to be able to write everything in it, as much as possible anyway. But that meant there was a lot that we had to do to enable that. But before I go on to talk about that particular issue, really why Python? Well, these are somewhat facetious goals, not entirely, but a little more seriously. The escape from IRAF. So the key thing that it let us do was, in giving us something that we could run IRAF tasks from, it allowed us to integrate software written a different way. It's extremely different to say, oh, we're going to write a new system from scratch. But here we could still provide facilities to all the IRF tasks and begin slowly integrating new ways of writing software. So this is what I meant by Trojan horse. It gave us a way of gradually moving away from IRF without causing huge disruptions. And it looked like, you know, if we could do the same kind of things IDL could do, we perhaps could do them even better. These two things, well, these things are actually, I think, overlooked. One is Python is a language that is very powerful for developers, but is accessible to astronomers. And getting those two classes of people using the same tools, I think, provides a huge benefit. It's not always noticed or mentioned. Obviously, there's a huge amount. You know, we broadened the suite of tools that we could make available by using a language that involves a much bigger community. Just not in science, but also in just general, things that you need to do when writing software. And something else that I think, learning from the Python community. When I went to the first Python conference, I was struck at how differently software was done in that community. And I think, what I learned from it is that they had a lot to teach us in how to make a lot of progress as a community in cooperative efforts. So it's something that I think just makes it more satisfying to write software in. And I don't know, how many people have seen the Peter Wang video on Python evangelism? Few people. I recommend you Google Peter Wang Python evangelism video. It's well worth watching because he makes some important points. One of the things he mentions is a moxie factor, which is the feeling that you can accomplish more, that you sort of have a greater ambition to do things in Python than in other languages. And that's actually a very important thing. So what I was referring to in the things that were, I think, missing from Python that would enable us to write applications in were sort of these three big areas. Array manipulations. It had something called numeric, but numeric wasn't quite there. And eventually we ended up writing our own called numarray, which in turn spurred Travis Oliphant to rewrite numeric, completely rewrite it to what we know now as numpy. And although it seems kind of chaotic, it was, I think, couldn't have turned out better for us because we don't have to support numarray. Somebody else does that. So in the long run, it was a big thing for us. Dealing with FITS files, there wasn't really any complete tool at the time. So we took it upon ourselves to take Paul Barrett's PyFits and extend it to use the new array facilities. And it's something, a lot of what we wanted in PyFits drove the features that are in NumPy, really. Structured arrays, things like that, being able to do efficient operations on large images. And finally, visualization, even just simple plotting. It was a real mess at the time. There were a large number of packages available at the time, but all of them had serious flaws of one kind or another. And so we started out on Chaco. We were working with Enthought, and when that didn't seem like it was going to yield what we needed, we became involved, seriously involved in doing the Matplotlib thing, and that's turned out extremely well. So for HST, where we started using Python as an applications language was in these were sort of the first major projects that we were actually developing applications in. And then we ended up also rewriting the ETCs for HST in Python. So there was a fair amount of work that went into that, all those things. And gave us experience with, how to do things in that area. But one thing I would say is that doing things for operational purposes is somewhat easier. What you have to do is generally narrower, more focused. But if you want tools to be used for general data analysis, they have to be broader in scope, they have to be easier for astronomers to use, and that's a harder problem in general, I think. And there are still a lot of useful IRAF tools without corresponding functionality in Python. And another thing we have to consider is that these, they need to be broader than just what HST and JWST need. HST never really gave us the resources to do much about this. Anything that we did to help aid data analysis is sort of incidental to dealing with HST projects. JWST, I think, has changed the picture. So yeah, as I say, it comes into the picture. Here's a paper mache model, full-size paper mache model of JWST. To give you an idea of the scale of what it looks like. So what is the role for JWST? Well, above all things, we're tasked to do calibration pipelines. And we learned a lot from the HST pipelines and things that we wanted to improve significantly. For HST, pipelines generally were done independently. Sometimes they copied code from one to the other. But it very often ended up they did things inconsistently for no real good reason. They often used inconsistent standards, different algorithms for basically the same kind of thing. Later on, when we got into dithering and mosaicing, the WCS issue became a very painful issue for us. I think it probably cost us at least an FTE or dealing with all that, all the pain it entailed. One thing that HST did was spend a lot of time writing tasks to generate reference files, and these are used by very few people. It's sort of a waste of developers' time to do things that really astronomers are better suited to generate. So that's something that we're trying to avoid this time. We want to give the tools to do it, but we don't want to do that kind of thing ourselves. We always struggled against the limitations of FITS, and the recognition that over the course of the mission, you often learn there are a lot of algorithms and steps that you need to change. So flexibility is very important. This is a case of premature optimization. So initial performance is not the most important thing to worry about. For data analysis, we have some new observing modes that HST doesn't really deal with. Particularly, I'm highlighting here the MOS and IFU spectroscopy. And when the launch was delayed significantly, it provided an opportunity to do something about it. So the case was made that maybe we should take seriously the idea of replacing some of the IRAF tools, important IRAF tools. We never said we were going to replace everything. Did they really want to believe that people should use IRAF through the whole JWST mission? And so surprisingly, at least surprisingly to me, the request to do this was well funded. And they gave us significant resources to do this. This does not happen very often in funding, I think. So I would hate to see this opportunity wasted. On the other hand, I always worry about these sorts of things. The resources that are dedicated to data analysis, you have to understand that they tend to be viewed as relatively low priority in the mission compared to everything else. So if something goes wrong somewhere else and they need resources, they may want to take them away for that. There are political issues that sometimes they want resources for. If there are budget problems, it may be the first area they cut. And at the same time, HST funding is decreasing, so support that we got for supporting some of the standard tools that we'd had before now is sort of evaporating, and so that's sort of drawing away for what we can do for JWST. But I'm, in some sense, more worried about the latter item, which I'll have a slight digression on, which when I say process entanglement, I mean essentially bureaucracy. NASA, especially at this stage, is very interested in doing lots of detailed schedules and requirements and things like that. So I thought it'd be good to sort of stand back a little bit and consider what the history in this area has been in relation to that. So I've listed what seems to me. If anybody has better examples, I'm all open to hearing about these. Things that I think have generally been viewed as successful projects. I would say most of these did not have much formal program management, at least at the beginning. And there are some here that had virtually none. I can say that in our case, PyFits, PyRef, NumArray, NumPy, Matplotlib, a lot of our AstroPy work had almost no formal project management oversight. And that's true for a lot of the STScI and tables work that went on as well. On the other hand, I'm trying to not get too specific, but I'll talk more about the first because I know something about that. Interestingly, for HST, a lot of work, a lot of the early work had very formal processes, lots of requirements, lots of scheduling and planning and all that stuff. And all the work that led up to the point before they decided to use IRAF was essentially thrown away. Completely thrown away. Years of work just tossed. And at that point, I'd say, and I don't think it was true just for, it happened in a lot of areas at the Institute. The launch was getting closer and panic set in, and suddenly they started dispensing with a lot of the formality because they just felt they weren't going to be able to get done.
Would it be fair to say from this that the successful projects had community support and then?
That could be, you could also argue that some of them, the initial work was very flexibly oriented. You try this and do that, and maybe it had a lot of feedback and maybe it didn't.
Sure.
But at least it wasn't encumbered by a very rigid plan. Mm-hmm. And so no doubt there are other factors. I mean, all these things are complicated things, but I do have trouble thinking of a very formal thing that involved a big suite of tools. I'm not talking about a single application that somebody wrote this way, but something that is fairly broad and encompasses many tools that one could use. So about not long, so that's my digression on this. So I mentioned this, I'm not going to talk about it because Eric discussed this in great detail, but it's something that we had been hoping would happen, and was important for us for a variety of reasons. If nothing else, to get other sources of information. I'll spend a little more time talking about why I think this is important for what we'll be doing in the future. But I think AstroPy is a very important aspect of what JWC needs to get involved with. So let me talk a little bit about the JWC data analysis plans. I'll be going into detail on various things, a little bit more about things that I think are the harder issues that we have to face at the Institute anyway. There's some overlap with the calibration pipelines. I mean, WCS issues, fitting, file format issues are things that, and they're also data analysis functionality that's also useful for calibration. So it's not one or the other really. There tends to be a significant overlap. We would like to make it as generic as possible. Something I've stressed to the project people is that if you just make a data analysis system useful for one telescope, people will be very disinclined to invest the time to learn it. They need to use it for other things and they want to compare their data to data from other telescopes as well. So it doesn't mean that we will do everything for everybody, but we have to keep the design open so that it's easy to support other needs like that. And also maybe show examples of make it easy for other people to extend. I think modeling is a little bit of example of this. You know, it's an object-oriented framework and things, but if you provide a template, examples, models, you say just do this. It's not terribly hard to add your own. Units would be a very simple example of adding if you needed your own custom units. Things like that. Show a way of doing this that won't incur a high overhead and use AstroPi as a focus. We want all this stuff to be open source. We want it to go and enable contributions to the community, contributions in multiple ways. Again,
Is that public knowledge? Like, is there a document, a public document that, I mean, this is actually, in my opinion, a big deal, that the JWST data analysis plan includes an open source package as the focus?
I'm not sure that it's not a requirement as far as NASA goes, and I don't know where they, I mean, in our reviews, I make this, you know, I say this over and over again. It's a little funny. One of the reviews I had to do had a lot about AstroPi in it, and they said, take it all out. Seriously. And then when I took it all out, then they said, no, you're talking a lot about really things that are AstroPi. You should, I'm not kidding.
I mean, I don't think the wider community recognizes this issue.
I'm happy to say it publicly. I'm not sure what the forum for that is, but yeah, this is where we want things, either in the core or affiliated packages, but we want things to be people can contribute to. It's open source. It's consistent with AstroPi.
I mean, I would suggest this is something that the science staff at Space Telescope need to be talking more about.
Okay.
The ones that are, when they go to conferences, they're going to be saying this. And that's the way that the rest of the community is going to hear about it.
So you've heard, I'm not going to talk very much about this because I think we've already covered these topics already. The only thing I think I might say a little bit is the WCS, some people wonder why that's such a big deal for us. And the reason it is that more and more people want to work with the original sampling of the data. It may be calibrated, but it's not resampled. And that enables, some cases forward modeling or, Bayesian analysis. Or if you're finally going to do one resampling, you can always go back to the original thing and all the information is packaged there. You don't have to go searching around for reference files someplace and do this. We want this information to be tightly bound to the data. This is a list of the, this is not complete, but this sort of illustrates some of the main areas of focus for JWST data analysis. They're very interested in being able to deal with data cubes and multi-object spectrographs and visualization and analysis. So that's clearly one of our early focus, being able to do spectral model fitting and things like that. PSF matching is something that's been mentioned many times. JWC has a wide range of wavelengths. PSF changes a lot, plus using it with other telescopes and instruments. So that's a fairly big deal. It's not a simple problem to solve. Coronagraphic reduction tools, that's something that will need some sophisticated things available. But then there's some more mundane things, image utilities, things that IREF has that it's not quite as easy to do in Python. Or there's not a unified interface or something like that. Source identification characterization, there's a fair amount of work going on that already. And a little bit on sort of the general approach that we see. This is not just about replacing our functionality. We're not just, if there are other things that are needed and they're high priority, we'll do that too. But when we are replacing our functionality, it's not, we're going to make a task that behaves just like an IRF task. We need something that does something similar, but it may do it differently. And also, we're not doing the sort of IRA approach of big monolithic black box application or tasks. We could do some of those, but basically they need to be accessible. People need to be able to customize them, and they need to be able to access lower levels of functionality at different levels of library. So, sort of you provide things at low levels for people who are familiar with the details and want to do things their own way, all the way up to sort of high level functionality. And use as much existing functionality elsewhere. Don't reinvent the wheel if you don't have to. Sometimes, though, as examples in SciPy and others, they don't always have the same interface, and you want to be able to provide some sort of convenient, consistent way of using these tools, especially if they come from different places. I'm going to talk a little bit. So one of the things that we have not had a lot of experience with at the Institute is interactive tools. It's an important use case, but the thing is, in my experience, GUIs are very expensive. And the typical numbers, it's an order of magnitude more work to do a good complex GUI. And it's easy. There's a high expectation among many users that, I want to use a GUI, but they just aren't aware of what the cost is. It's easy to burn a lot of resources on it and end up with something that's not going to be long-lived. If you think about it, how many GUIs out there have stood the test of time in astronomy? Not a whole lot of them. DS9 is the most obvious example. But there have been a lot more done than have actually survived. And part of that, I think, is it's easy to make quick progress, but the effort grows very non-linearly. As you add features, interactions between all the features, it suddenly grows very difficult to try and keep all that working properly. So the maintenance on these things is, so you can write this, but you have to keep expending a fair amount of effort to do this. So, as I said, this is something I'm concerned about. I think to be successful, we have to be very careful about limiting, what features we put in there. We make it extensible by other people, by plugins and things, but, one thing I do not want to see is all the data analysis resources suddenly sucked into doing GUIs. We have to make sure we partition that at a certain level. This is one area I think IRAF was very, very smart in that they have somewhat primitive interaction schemes, but that allowed them to do a lot of functionality without spending a lot of time on that. There are all sorts of questions that come up in this. What technology to use? Web-based, desktop. The web has certain advantages. That seems to be the current trend. It's certainly obviously good for remote use. On the other hand, it means we have to write JavaScript. And I always have this worry, there's sort of this, more and more as people do things like that, they go, we should, be able to plot this in JavaScript, or do something else in JavaScript, or deal with units, or this and that. And then you see yourself more and more replicating functionality in another language, and, can we really afford to do that? Another thing I'm not sure a lot of people realize is that web technology is rapidly changing. And if you want to get involved in it, you better be ready to keep up. I think there's generally a much higher cost of keeping up, maintenance. Maintenance, you may be forced to rewrite a number of things as time goes on, and that's something that you have to do. Perhaps some performance penalties. I mean, there's a lot of work in that area to solve that problem, so I don't know if it's a real issue or not. So, for desktops, the pros are, we can do this all in Python. We don't have to deal with, communication issues between JavaScript and Python. We have a number of tools already existing as GUIs that we can leverage, and I'll talk about that more. The worries had been that the whatever framework you use could be a difficult thing to install. and that, again, maybe the world is moving to a browser as an interface platform. But in the end, our initial development is going to be desktop GUI, mainly because a lot of work has already been done on it. I would like to show a lot of progress reasonably quickly rather than spending a lot of time re-implementing things in a different, a web platform and sort of ending up where we were 2 years ago. I think binary packages like Anaconda will solve the framework installation problem. In any case, we have to install Python on the local machine. So it's not like you avoid having to install software. That's, I think for data analysis, that's going to be necessary in almost all cases anyway. So if desktop, it seems like Qt is the obvious choice. And it's a modern and highly, generally well-considered framework, cross-platform. And it's also supported by two of the tools that we're very interested in using, namely Glue and Ginga. Reusing this will save us a lot of work. So you've heard about Ginga. I'm not going to show anything about that. Eric has set it up pretty well to handle plugins to customize it for the needs. And it's already been modified, both sides, that it works within Glue. So you can use it as one of the available viewers inside of Glue. How many people have seen demos or have heard about Glue? Could you give me a show of hands? Not, okay, some fraction. It was a tool developed at Harvard by Chris Beaumont, and its sort of main goal was to show linked views of things. And I'll run a little video that illustrates it. I think we'd like to use it for, and not just that purpose, it's a useful thing in that, but I think it has a nice role in showing you visualizations of data that intrinsically have linkages, and that I think is true for cube viewing, and also multiple object spectra, would take use of this kind of facility, so that's why we're very interested in it. What we're also interested in is that having it work such that if you're working in a terminal environment, you can send things to it, do things in it, and so that you can sort of work in parallel between this, that you don't have to make it your central focus of analysis. A lot of people would like it to work that way. So this is just a sort of little video that shows after some point that if you select a region in this image, you can see what data points in these plots are affected by the selection and vice versa. So you can see there's a square region being selected there, and then in red you see the corresponding items in those plots that correspond to the spatial region you just picked out. Or you can go over to that, pick out elements in that, and it also allows putting in all sorts of data. You can define what linkages you want between this data set, this table, what corresponds to what. Very common, you want a spatial to an object connection. As long as the object has an RA index or something of that nature, you can relate it to an image display or do the same thing in wavelength, things like that. Interactive modeling is currently a focus, and the ideas here is to sort of basically supply the S-plot kind of functionality in IRAF. Being able to basically show spectra, residuals, models on top of that. Select features or regions that you want fit, or use it to determine initial parameters for fitting. We have a separate coordinating widget to interact with the models, so that you can add to the models, add lines if you want, add continuum, absorption lines, things of that nature, so that you can actually manipulate the model through the GUI and have these two things talk to each other. We'd like to keep these sort of as generic as possible, because you could use it for time series or something else. You may want to fit something spatially. So, and again, try to keep the features from growing without bound on these things. This is just sort of a screenshot of a prototype that have been done by some people at the Institute, where, you know, here's a case of selecting a spectral feature. This thing here shows you what model parameters of it, what the model components are and what their parameters are. Thing on the right shows you the various data elements. So I'm moving to the sort of last issue. I think is another challenge, I'll say. It may be it's probably surprising to a lot of people that it's been a long-standing problem of ours in getting engagement with our science staff in almost any software that we write. They generally have a lot of other priorities that often, for the same reasons I've discussed before, mean that they have relatively little time to devote to dealing with data analysis or even calibration pipelines. And so it's a perennial thing that you know, we sort of desire more interaction, but we can't get it, or not enough of it. And that may seem surprising, but it's absolutely the case. And so at the moment, they're trying to use something called sprints. I think it's a misnomer in this case, but to try and get staff to come and say, okay, you spend 2 weeks, we'll concentrate on defining what the priorities are for this tool. You work with the developer and they'll do some initial coding and things like that, and to get feedback to do that. We've done 3 of these, and they've been very useful for figuring out what needs to be done. They've been using Trello as a means of discussing what features and tasks should be done. As I said, these aren't sprints as software people usually think of, but it's been very useful to do. On the other hand, they've had to, even for these first few, they have a lot of trouble finding volunteers to do this. So I think it's not unlikely that they won't be able to sustain this. You know, even on the first few, it's been difficult to find people to do this. So I'm very worried that it's going to sort of peter out for a lack of available staff interest and time. And so I tend to think that we would benefit more by involving people outside of the Institute in developing these tools. That's a little bit, that worries people in the program management side. But I tell them, you know, most of our useful feedback is from outside, not inside. We get people to try these tools out. We get more feedback from the Astronomy community in general than we get from staff. And I think that's very likely going to be true for these things. So what I'd like to find, so they're a little nervous about this, but I would like to be able to say, I want to find some people out there who want to use this thing, need it for their science, are willing to work with us, and they'll help drive the priorities, you know, because better somebody there than no one. So that's...
And people you don't have to pay.
That's right.
So, this is good, but I wonder if you could maybe reorganize things a bit to get more engagement from within the Institute.
Oh, yeah. Go ahead.
I found personally that, I mean, I'm probably in a somewhat similar position to these guys, and, you know, I tend to blog things that take multiple days because I can't fit them in, but with my personal research, I've found that, you know, if I try to take a block that's a week or 2 long, I just can't fit it in because there's other pressing stuff that has to be done, so it gets delayed until, you know, the last day or something, and then I've got all the stuff being done. But if I take regular Fridays to do research, then, you know, I can always postpone things by 1 day usually. So.
Possibly.
The trick is to keep
Yeah.
the notes. So
Yeah.
let's go.
It's tricky. This is one reason it's hard to meet, you know, with the formal process. We don't control people that we have access to. Yeah, it's a difficult problem. So anyway, I in the near future, I would like to begin to solicit people that are, you know, in the general community sort of becoming involved in this process. And so my I guess a few random points. I'm almost done here. I thought I'd mention some things that may not be entirely obvious. I don't know, I should be mentioning the first one in the sense that maybe I think some people know what I mean by this, which is if people really knew how much work some of these software tasks would end up being, they might not have started them. So in this case, ignorance is a good thing. Do not, yeah. That's all. We should encourage more ignorance in this area. Do not, yeah. I've seen so many cases of people spending a large amounts of time trying to come up with the perfect design, the perfect set of requirements and things like that. Oh, just don't do it. I mean, it's worth spending some time doing it, but don't get carried away. You'll learn a lot more by doing a first failed implementation than spending a long time trying to figure out. You're never going to get it right without actually trying things out. Another aspect, and I think this is something that the astronomy community sometimes runs into when working in large groups, trying to get, again, come up with the perfect things. I don't know if people are familiar with the phrase "worse is better." There's an essay, a famous essay. If you Google it, you'll see what it means. It's basically making the point that you're much better off getting something that's somewhat useful out there. It may not be perfect, and the feedback that you get from it and the contributions that eventually end up with a much more advanced tool than somebody spent years and years polishing. Persistence is important. Just being there for a long time, supporting things, interacting, means a lot. And finally, to echo a little bit, I think what Wolfgang was saying, and this sort of comes also out of that Peter Wang talk, is only get people involved in Python that are really open to it. You don't want to force it on people that are unwilling to do this. They have to be very interested. You don't, otherwise you're sort of setting yourself up for failure if you unnaturally force it on people. And so I thought I'd end on, I think apparently videos are important, so I thought I'd end on a Python generated video to end the talk, and I can take questions just as soon as I start this. Anyway, so thanks for, thanks for, I hope we're not like these guys who get stopped by one police car. So